And so it's really nice to be here, and I want to thank the organizers for giving me the chance to speak. So let's get started on the talk. And the title is Asymptotics of Positive Harmonic Functions on Cylinder-like Domains. And this is joint work with my advisors Alex and Srinath. Okay, so I will organize, give a basic introduction, and then state the theorem and give idea. Okay, so here's a basic problem. So you have an unbounded Lipschitz domain, omega, in Rd, and you're given a positive harmonic function. So U is a positive harmonic function here, and it vanishes on the boundary of your domain. Okay? And what are the quantities we are interested in? So we want to measure the growth of U. So one way to do this is to introduce M of R. M of R is the supremum of U on the hyperplane x equals R. So you take your domain, intersect with this guy, and x equals R, and you take the sup over the section. So the question is, what is the growth of M of R as R tends to infinity? The general results will tell you that M of R tends to infinity, but we are really interested in how fast or how slow. What can you say? So our first instance, let me give you an example, and this is probably the only example when we know the exact growth. Okay? So take your omega to be a Lipschitz cylinder. So what do I mean by Lipschitz cylinder? The rest of the talk is the following. Omega equals R cross Lipschitz bounded domain in Rd minus 1. So this is what I would call Lipschitz cylinder. So let's consider this problem. U is positive here, harmonic, and vanishes on the boundary. Okay? And in this case, exact solutions are known. All solutions have to be of the following form. So for some constants A and B, these guys are A e to the square root lambda x plus B e to the minus square root lambda x times F1. Okay? Here is the x direction, this is the y direction. And what are the meaning of lambda and F1? Lambda is the first eigenvalue, so you solve the digital Laplacian in your D, and that's the first eigenvalue, and F1 is the eigenfunction that corresponds to this eigenvalue. Okay, so if you plug in x equals R, so you measure the growth at this section, you get a constant times the exponential section. So in this case, we know the exact growth. Of course, in general domains, you cannot hope to solve it explicitly. Okay, so you can best do only asymptotics. So this is what we are attempting to do here, to get asymptotics in domains which look like a cylinder. So I will define what are cylinder-like domains. Okay, so throughout this talk, omega is unbounded Lipschitz domain. And what we're going to do is we define a section, omega t, for t positive, to be the guys in omega that lie between two big chunks. So take the hyperplanes x equals t over 2 and 3t over 2, and you want to think of t as something really big, so that your domains are, remember, we want to get asymptotics at infinity. Okay, so now omega is called cylinder-like if there is a positive Lipschitz function A on 0 infinity, and we require a family of Lipschitz cylinders Ct such that on every compact, the Hausdorff distance between gamma t and Ct tends to 0 as t tends to infinity. So let me explain the terms here. What is gamma t? Gamma t is the big section omega t minus t times E1. E1 is the unit vector in the x direction. So 1, 0, 0, so on. Okay? Divided by this factor A of t, your Lipschitz function. So if this is close to your cylinder, then we call it cylinder-like. Okay? So what am I doing here? Omega t is this big chunk. When you do minus t1, you're translating it by t units, and then you're scaling by a factor A of t. So roughly, what these guys want, I'll come back to this. So roughly speaking, cylinder-like domain is one in which you translate big faraway portions, and then you scale it by appropriate constant, then it has to look like a cylinder. Okay? Yeah.
So I'm a little bit confused. Is the aperture opening up, or is it really cylindrical? I mean, it's sort of, it can be something opening up.
Yeah, but the thing is, here you don't want, here's why I put the condition A prime your ellipsis function derivative tends to 0 because you want your domains to have kind of a flat boundary. Otherwise, you cannot, if it grows too fast, you cannot hope to rescale it to a cylinder.
So it could be opening up logarithmically or like
yeah.
t to the 1 minus f.
Yeah, exactly. So I'm going to give you an example. So these two conditions here, I will show two examples, and this is, they require some conditions on your ellipsis cylinder. All of them have ellipsis constants bounded uniformly above it. So let's look at an example. This is what exactly he said. So our example is going to be a paraboloid. Okay? Take a paraboloid in RD, absolute y less than x to the alpha, and alpha between 0 and 1. So here's the condition why we need this thing here. If your domain, so here, your boundary, look at this, that's x to the alpha. So when you take the derivative, it goes to 0. Okay? If it grows too fast, then you cannot hope to rescale it to a cylinder. Okay, so here are the sections, the big chunks between far away portions, and we take our function to be t to the alpha, then our rescaled domains look like this. Okay? Absolute y less than 1 plus x over t to 1 minus alpha times alpha. What happens now? You fix a compact and you look above. Okay? So if t tends to infinity, what happens? This term becomes 0 because we are conditional on alpha. And this guy becomes the whole way around. So if you fix a compact, in that compact portion, absolute y less than 1, okay? Which is just the unit cylinder. So on every compact, gamma t converges the unit cylinder R plus P. So in this case, your cylinder-like domain, the families that you have, is just one cylinder. Okay? So this is our basic example, and here is our theorem for the asymptotics on cylinder-like. So our setup as usual, positive harmonic and vanishing on the boundary. And we have M of R, the quantity we defined before. It satisfies the following estimate. Logarithm of M of R is a certain error term times your main term, which is the integral from 1 to R dy over A of y. Okay? And this error is captured by this guy here, that h2 is a function that has, when you compare it with the main term, it tends to 0. And h1 is, again, some guy which has limit, finite limit at infinity. Okay. So I'm going to explain the basic ideas of the proof in the example of the paraboloid that we discussed before. Okay. So to just keep idea simple, take any sequence Tn goes to infinity. And I'm going to draw the big chunks Tn over 2 and 3Tn over 2. So let's look at this. This is our gamma Tn, the rescale domain. Okay? And what are we doing here? Remember how we got gamma Tn? We translate it to the left by t and then divide it by t to the alpha. So if you do the reverse operation, first multiply t to the alpha and then translate to the right, you land up here. So the idea is, we are having a harmonic function here. Using this map, we could construct someone harmonic here, and then we get the asymptotics for a cylinder, because these guys look like a cylinder. Okay, so here's the thing. So this map maps these almost cylinder-like domains to here, and what we can do now is define new functions on your cylinder, almost cylinders, Vn, which are defined by this guy. Okay. So what happens? So this is, you should just think of this factor here as a normalizing factor. Okay? So notice a few things about these functions Vn. Each Vn is positive, harmonic, okay? Because when you take the Laplacian, what you get is just a scalar multiple of the Laplacian of V. So you know, since Laplacian is 0, Laplace Vn is 0 on gamma n, Vn of 0, well, if you plug in 0, this term becomes 0. And so you have u at the x-axis, Tn, but you're dividing by the soup of the whole section. So you get Vn of 0 less or equal to 1. And finally, because of these boundaries corresponding, this portion goes into this portion and so on. And so we have Vn equal to 0 on the lateral portion here. Vn's are 0 here and here because these guys go here and here. Okay, so now we may extract, this is a classical theorem, you just quantify slightly and you get that if you have these conditions, then you can extract a subsequence. I'm still going to call them Vn, which converts to a harmonic function uniformly on the complex of the cylinder. Okay? So here's a picture. Let me explain this again. That we have these gamma s, these big liters are your guys standing to the cylinder, and so we can extract a subsequence Vn which converts here. But then look, Vn is 0 on the boundary, and Vn are tending to V, so one guess would be that the limit function vanishes on the boundary. Right? You have Vn's, they are tending here, and these guys are tending to cylinder, so you would hope that your limit function is 0 on the cylinder. Okay? So we proved that, in fact, this is the case, that your limit function extends up to boundary and vanishes. Why is this useful? Okay? And I have to mention here that this proof is probably the most tricky part of the whole thing, and it uses the boundary Harmonic principle and also the Holder estimates near the boundary. So why is this useful? Because look, now we have that our limit function is positive harmonic and 0 on the boundary of cylinder. So what do we have? We know what is exactly the solution look like. We discussed in the first slide that the solutions are like this. Right? And let's go back to one of the definitions of Vn. Vn are defined like this. They converge to V. Right? So let's go back to the picture here. So we know that Vn converges to V. Now let's look at one particular X section. Okay? In this X section, I've drawn this here. Your Vn and V are towards the boundary. Here, these guys are 0. Right? So again, by boundary Harmonic principle, their supremum in this section is obtained away from the boundary. So in this relation, in this convergence, we can take the sup of Vn's along x equals r, and you will get the corresponding, they will tell you the corresponding supremum on for V, the limit function. Okay, so what this gives us when we take the supremum is this. The m, remember m is our supremum of sections, so m of Tn to the alpha r plus Tn divided by m of Tn tends to e to the square root lambda r. So you may wonder, well, when I take the supremum here, you have a term with square root lambda r, and you get another one with the negative square root lambda r, but this guy, coefficient b here, has to vanish. Why? Let's look at this. The left-hand side, let's plug in r to be a negative number. Okay? If you plug in r to be a negative number, so this argument inside the parenthesis is less than Tn, right? Because alpha is less than 1. So this is something less than Tn. You're dividing by the supremum on the section x equals Tn. So by the maximum principle, so when you go here, this has to be less than 1. So that's why if this guy doesn't vanish, when you plug r, negative number, because it doesn't vanish, it will blow up. Okay? But we know the left-hand side is bounded by 1 if you plug r as negative number. So that's why b here has to vanish. Okay? And again, what happened to the a guy here? Well, you plug in r equals 0, you get left side 1. So again, you have to get corresponding right side 1. So that's why it's this. Okay? So far we have this convergence. Our last step in this is to show that when if you have such a convergence for every sequence Tn, okay, then you can write m to be of the following form. So anything that satisfies this for every Tn as m of r equals exponential of square root lambda over 1 minus alpha minus r to the 1 minus alpha plus an error. The error satisfies this. So notice we get slightly better estimate than the one in the theorem, but this is because we're restricted to a specific case. And let me mention that such problems, when you have to decide the asymptotics, these guys are also of interest to probabilists because they are interested in stuff like harmonic measure estimates, that's a probabilistic interpretation, and also about random variables, how can you get the integrability conditions on the exit time or the exit distribution, and so on. Okay. And I want to mention that, especially in the case of a paraboloid, Rodrigo Banuelos and Tom Carroll, they prove the exact estimates using probability, but our method is different, and then also we get it for more general domains, not just a paraboloid, but anything that's basically cylinder. And last but not least, I also want to mention that we have asymptotics also for domains which are cone-like. This is corresponding, we have a cylinder-like domain here, and what we managed to also obtain is, roughly speaking, cone-like domains are guys which, when you rescale, okay, you also get something that looks like a cone. Because even for cones, we can get the exact solutions. So we have two classes. One is for cylinder-like, and the other is cone-like. And we have similar estimates for also cone. And yes, that's it.
The way I would think about that problem, I was trained in physics, so I do hand waving, would be via the WKB approximation. That it seems that if you have something that's a cylinder, that your wave function should be roughly the lowest eigenfunction of a Laplacian in the transverse direction and some function in the linear direction. And then what you wind up with is a Schrodinger operator, a one-dimensional Schrodinger operator for that linear function, for which the input is the eigenfunction, the eigenvalue of the Laplacian in the transverse direction. That's going to be roughly 1 over a squared, and then since you're asking for a zero energy thing, you're bounded away from that, and you can use your WKB analysis, and you integrate the square root of the energy difference. You're integrating 1 over a, and that gives you your rate of growth. Now, I'm wondering whether you can first of all take that kind of hand wave and relate it to the rigorous estimates that you've got, and perhaps use that kind of approach to get error estimates. Because WKB theory is very well developed about how accurate is it.
So this is something that I've not explored. I mean, we think that the error estimates, so far we only managed to obtain these kind of error estimates, but our conjecture is that this error term should be actually little o of 1. And that is something that I have not, the method that you suggested that I have not explored it. But our conjecture is that this error term is, what we have here is too strong. We expect little o of 1, so something that just takes too strong. But at this point, I'm not sure. I have not explored the idea, but
can I just interject something there? So I think that what you're saying, you translate into this thing, you get a one-dimensional problem on the half line, but with very slowly decaying potential, right? So, right. And then the question is, exactly that. Even if that operator is very non-trivial to say, exactly what the rate of decay of solutions, or what the rate of growth of solutions is. It's fairly. So this is this one of the question gets like that. Why did you know it's important?